Okay, so you want to know about linear span. Okay, before beginning linear transformation, I'll go towards linear span. So welcome all to week 2 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IUR IIT Bombay. So I'll try to solve some problems related to the problems that are posted in your assignment for week 2, and would like to clear any doubts that you have in the topic. Okay. Okay. So somebody asks, what is a linear span? Okay. So first of all, let's say you have two vectors. Let's say you have some v1 which is equal to 1 2, and there is some vector v2 which is equal to 2 3. Okay. So now like let's say if you multiply your first vector with some number, let's say 2, and add it to let's say 3 times v2. So this kind of combination is something that is called as linear combination. Okay, so you are linearly combining these two vectors. Okay, so you are taking some scaling of the first vector and you are adding it to some scaling of the second vector. This kind of thing is called as linear combination. Okay, so what would be the result? Result would be 2 plus 6 8, and 4 plus 9 would be 13. So this is a vector that you obtained by linear combination of these two vectors. You can obtain many such vectors. Let's say you did 1.5 times v1 plus v2, or you did any alpha times v1 plus alpha times v2, alpha 1 alpha 2. Okay, so these are the linear combinations of vectors that you can do. Okay, so what is actually a linear span? So let's say you have vectors v1 and v2. Okay, then linear span of your set v1 and v2 is set of all possible linear combination of these vectors. Okay, so if you take all combination, let's say let's say v1 plus v2, you take 2v1 plus 2v2, and so on. So you take all possible linear combination of your vectors, then whatever you obtain is called the linear span of your vectors. Okay, so this is what is meant by linear span of vectors. Okay. Okay. Anybody has anything else to ask before I can like start whatever I have prepared? Okay, I'll begin with whatever I have prepared. Okay, so now in the first week, what we learned was about vector spaces. So spaces that have some special kind of property, we call them vector space, right? Now, in the next week, what is covered is it is like the next week talks about functions between these kind of spaces. Okay, these functions also have a very nice property, that is they can be represented as a matrix, and then all the calculation that you did in matrix in your high school can become handy over here. Okay, so so we have a special kind of a function. So what is a linear transformation? Linear transformation is a function between two vector space. So let's say we have v and w as two vector space that satisfies these two properties. Okay, so let's say if you have some vector v1 and some vector v1, if you take a map of v1 plus v2, it is nothing but you individually mapped them and then you took their sum. Okay, so like let's say if you look at some function, let's say x square, and then this property is not satisfied, right? So if you take, let's say, f of 1, this is 1, f of 2 is 4, but if you take f of 1 plus 2, it is f of 3, that is 9. So if you sum these two things, this is not equal to the function of sum. Okay, so any function that would satisfy this property is called a linear transformation. Okay, so these are the two important properties that you need to remember. Okay, now there are some terminology or fancy terms related to linear transformation. that you might encounter at many places. First is something that is called as linear operator. Okay, so linear transformation is nothing but a function from function between two vector spaces, right? So if that function is between the same space, so whatever is your domain, the same is your codomain or the range space. So then your linear transformation is called as linear operator. Okay, this is just a fancy term. Okay, now let's say your vector space V was over some field F, and if your linear transformation is from your vector space V to that particular field F, then that kind of linear transformation is called as a linear functional. Okay, this is just some basic definitions. Any doubt with definition of linear transformation? Okay, so we want to prove something. The first question is prove that. So if you have a linear transformation, you have to prove that the map of zero element would be zero itself. Okay, so this property is something important to remember. So when you are trying to solve questions where you need to check whether something is a linear transformation or not, this property is many times becomes handy. Okay, so if you just use this particular property of linear transformation, many options you can directly eliminate. Okay, so how can we try to prove that 0 is getting mapped to 0? So let's try how we can prove. So let's say let's see what is t of 0. Okay, so t of 0 can be written as t of 0 plus 0, right? Now by the property of linear transformation, what we know is that we can split this thing. So this becomes 2 times t of 0. Okay, now if you take 1 t of 0 to the other side, what do you obtain? T of 0 is equal to 0. This is quite a simple proof, but this property of linear transformation is sort of useful. Okay, okay, so now we come to our first exercise. I think we have a question in this year's assignment also, which asks you to check whether some of the functions are linear transformation or not. So what you need to do there is, for every question, you just need to verify these two properties. Okay, and you can also use your trick that t of 0 is equal to 0 at some places to obtain your answer. Okay, so let's look at first example. First one says that t of a1 comma a2 is 1 comma a2. Okay, so just now I mentioned that t of 0 should be mapped to 0. Okay, now if we take t of 0, what do we obtain? We obtain 1 comma 0. Is it 0? No. So what we can infer, that our first example that is mentioned over here is not a linear map. Okay, and why is it not a linear map? Because it does not satisfy the property t of 0 is equal to 0. Okay, so the first example was quite a simple one. Let's look at the second example. What does it say? T of a1 comma a2, okay, is equal to a1 comma a1 square. Okay, so you can see there is a square term on the second side, so most probably that is the term that will create an error. Okay, now let's look at some very simple example. Let's take t of 0 comma 1. Okay, what is its map? This is a1 remains as it is 0, and the second terms become 1. Okay, now let's take t of 0 2. What is it? This would be 0 comma 4, right? Now if we take t of let's call it x1, let's call this x2, t of x1 plus x2, what it is? This is t of 0 comma 3, right? And what would be its result? It would be 0 comma 9. Now is 0 comma 9 equal to 0 comma 1 plus 0 comma 4? No, these two are not equal. So this also is not a linear transformation, because it won't satisfy t of x1 plus x2 is equal to T of x1 plus T of x2. Okay. So similarly, for the third part also, you can see that if you take a sine of a1 plus a2, it is not equal to sine a plus sine a2. Sorry, sine of a1 plus sine of a2. That would be the reason why this would fail to be a linear transformation. Okay. Now, in the fourth example, let's try doing fourth example. What is the map? T of a1 comma a2. This is mod of a1 comma a2. Okay. Now, let's say we take T of 2 comma 2. Okay. What would be its map? It would be mod of a1, that is 2, and again 2. Now let's take 2 of okay, let's try to do this some other way. Okay. So now if I take T of minus 1 times 2 of that would satisfy. Okay. Let's take this only. Okay, let's take T of minus 2 comma 2. What would be the map? Map would be 2 comma 2, right? Now if I take some of the like elements on the left hand side, that is my x1 and x2, what would I obtain? I would obtain T of 0 comma 4, right? What would be the map? Map would be 0 comma 4. Okay. Now if you again take the sum of quantities on right hand side that we obtained before, the sum we would have got is 4 comma 4. Are these two equal? No. Because they are not equal, this one is also not a linear transformation. Okay. Now in the last one you can easily check that what is the map of 0, T of 0 comma 0. It would be 0 plus 1 comma 0, that is 1 comma 0. So again in the last case also T of 0 is not equal to 0. So we should this is not a not linear transformation. This is also not. Why is it not a linear transformation? Because T of 0 is not equal to 0. Okay. Okay. So any doubt till now? Okay. Now I have two more negative examples. I want you to try at least example number 32. Okay. And tell me like two values of let's say if I have v1 plus v2, I don't want it to be equal to t of v1 plus t of v2. So tell me values of v1 and v2 that I should take so that we can prove that this is not a linear transformation. I'll wait for 2-3 minutes so that you can try. I want values of v1 and v2 using which we can prove that this particular transformation given to us is not a linear transformation. Anyone was able to solve it? So you can see that we have a mod over here, right? So if you want to like reduce to examples, so what we should like easily do is let's fix the first position straight away to 0. This is quite simple. Okay. Now whatever you are taking as the second position, for V2 just take negative of that. Okay. Now, yeah. Now if you do this thing, what you would obtain is that T of V1, what it is, 0 minus 2 times mod of 2. Okay, so this is minus 4, and the second term is 0 minus 4 times of 2. This is minus 8, right? Now what is T of V2? You would obtain the first position again as uh, this is 0 minus mod of this particular thing. So we would obtain this as minus 4, and the second position you would obtain as 8. Okay. Now if you take V1 plus V2, what it is? This is 0 comma 0, right? So what is T of V1 plus V2? T of V1 plus V2 is equal to 0 minus 0, over here also 0 minus 0, right? But what is T of V1 plus T of V2? T of V1 plus T of V2 is minus 8 comma 0. So because these two quantities are not equal, so this is also not a linear transformation. Okay. So just like informal kind of a comment. Why are these linear transformations very useful in machine learning? Okay. So many times the way in which you collect your data, right, or in the way you obtain your data, applying machine learning techniques directly to that particular space might not be very useful. Okay. Now, if you map that thing to some other space, then it might be very useful. Okay. For example, uh, this is not an example of a linear transformation, but it will give you a flavor why these kind of transformations are very useful. Let's say you have two kind of data. Let's say you have some purple points, okay, and you have some, let's say, red points with you, okay, and you want to find a classifier, a very simple classifier, using which you can separate these two types of data point, okay. Now, if you try this thing in, let's say, R2, no matter what you do, you won't be able to obtain a linear plane using which you can separate them, right? Now, there are two possible options that I can think of, okay. First is, let's say you lift it to R3, okay, in which for all the red points, you are mapping it in a such a way that the z-axis is 1, let's say, okay, and for all the purple points, you mapped it in such a way that your z-axis is 1. Rohini, I'll just finish this and then get back to you. Okay. So one way is that you can map it into higher space where they become linearly separable. Okay. The second option is then that you can look at the radius, right? The argument, the distance from the this particular center you can look at. So then if you map the, let's say, the distance of these points from this particular center point, then all the red points would be at a low distance from this thing, and all the purple points would be at a higher distance from these points, right? Then you can sort of separate it. So this is the idea behind this kernel function and those kind of thing that exist in your machine learning literature. Yeah, Rohini, you raised your hand. You had any doubt? Somebody was raising their hand in between. You have any doubt or anything you want to add to it? This whatever I said.
No, sir. Actually, my doubt is clear now.
Okay.
हाँ.
Okay. Thank you. Okay. Now, one advantage of linear transformation is that for every linear transformation, you can find a matrix representation of it. Okay. And on the other hand also, if you have some square, some any like even a rectangular matrix, you can find a corresponding linear transformation. Okay. So matrices and this linear transformation goes hand in hand. Okay. Now, so let's say if you want to see how these things happen, so let's say if you define your linear transformation such as that you are just multiplying this vector x with your matrix A, then you are just defining a linear transformation. Okay. So this is actually what happens. Now we will try to look at some examples where let's say if you have uh, some matrix given, how do you uh, obtain corresponding linear transformation? Okay. And we will see the other way around also. So if you have some linear transformation given, how do you obtain the corresponding matrix to it? Okay. Okay. So let's look at this particular example. Let's say you have some matrix A where you have this kind of entry, and somebody is saying that this A is corresponding to some linear transformation T. Okay. Now T of x would be defined as A multiplied with x. Okay. So for example, if you want to find T of 1 comma minus 3, what you would do, you would multiply A with 1 comma minus 3. So this is 2002 multiplied with 1 comma minus 3. Okay. So what would you obtain? You would obtain 2, and over here you would obtain minus 6, right? So this is what you would obtain as a result of this. Okay. Now what we actually want to do when I say that we want to recover the linear transformation from the matrix, what I actually mean is, can we, let's say if we have some arbitrary x1 and x2, what would be the map of this particular thing? So if you recall whatever examples we did here, we had linear transformation written in this form. So from the matrix, we want to write again in that form. So again, this is also simple. What we will do is we will just multiply A with x1 and x2. Okay, so what we would obtain is 2002 and x1 x2. This is nothing but 2x1 comma 2x2. So what is transformation of x1 comma x2? This is 2x1 comma 2x2. Okay. So just a recap of this example. So if you want to obtain your linear transformation from a matrix, just multiply it with some like arbitrary x1 and x2 and see whatever result you get. That would be your linear transformation. Okay. Okay. So here is the other way around. So now you are given with some linear transformation, and what we have to do is we have to obtain the corresponding matrix to this linear transformation. Okay. So now it's the other way around. So one thing that you should remember is that whatever matrix that you obtain would be with respect to some basis. Okay. So what you need to do is you need to select a basis over here, and you need to select a basis over here. Okay. So in most of the like real life cases also, and in most of the examples that you will solve, so it's very convenient to assume standard basis. Okay. So let's say for R3, what is our standard basis? This is 1 0 0, this is 0 1 0, and this is 0 0 1. Okay. And for R2, what is our standard basis? For R2, our standard basis is 1 0 and 0 1. Okay. Okay. Now how do you write this thing? Okay, in form of a matrix. Okay. Okay, some people are joining. Let me admit them. Okay. Now, what you will do is, so let's say your map is from R3 to R2. Okay. And you have selected a basis for R3 and an R2. Okay. The next step is find the map of all the basis element of R3. Okay. So, step is find map of all basis element of R3. So, whatever so is your domain, you will find the like the transformation of all those basis elements. For example, what is T of 100? This is A1 minus A2, so 1 minus 0 is 1, and 2 times of A3, it would be 0. Okay. Now, after you have obtained, okay, this map of first basic element, what you will do is, you will try to write this thing in form of these two basis element. So if this is for R2, so you try to write it in linear combination of basis element of your codomain set or the codomain vector space. So what it is, this is, let's say this is V1, this is V2. What it is, this would be some number times V1 plus some number times V2. So what are these numbers? So this is 1 times V1 plus 0 times V2. This was quite visible. Maybe we will see some examples where this thing is not very much visible. Okay. So just keep this thing right now. Okay. So now let's find the map of other element also. This is 0, 1, 0. Okay. So what it is, this is A1 minus A2. So this is minus 1. And again, it's 2A3. So it's 0. So again, we can write it as a linear combination of V1 and V2. What do we obtain? We obtain this to be minus V1 times, and this is 0 times V2. Okay. Let's look at the third one also. Let's quickly look at that. 0, 0, 1. So this is 0, comma 2 now, because it was 2A3, right? A1 minus A2 and 2A3. So what it is? Now this is V1 plus, let's say, V2. So this is 0 times V1 and 2 times V2, right? Now, after you have done this much, obtaining the matrix is very simple from here. Okay. What you will do is, whatever coefficients that I have written in green over here, whatever coefficients you have obtained, you will write them in column form. Okay. So what would be the first column of the matrix would be the coefficient of this first equation that you have got. Okay. So this would be 1, 0. Okay. Now what would be the second column? Second column would be minus 1, 0. Third column would be 0, comma 2. So this is the matrix corresponding to the linear transformation that we had. Okay. Just a very quick recap. What you need to do is, you need to select a basis for both the spaces. Okay. I selected the basis. Now I obtained map for every element of the basis and wrote them in form of basis of the other vector space. Okay. And then just wrote the coefficient in form of column vectors. Anybody has any doubt? I'll do one more example for this, but anybody has any doubt in this?
Sir, after
Yes.
selecting the basis, we have to map them in as a linear combination of codomain set.
Mm. So what you will do is, first of all, you will map them according to whatever transformation you are given, and then you will write it as a linear combination of basis of codomain set. Okay.
Okay.
Okay. Okay. So I think if we have some, okay. So I'll write this map. We have sufficient time, so I'll do this example also. So let's write this function. The question is, T of A1 comma A2 is nothing but a1 plus a2 comma 0 comma 2a1 minus a2. Okay. So again, this map is from R2 to R3 this time. Okay. The map is from this T is from R2 to R3. So what is the standard basis for R2? You can actually take any basis, right? But what we will do is we will for the ease of our life, because the calculations become very simple, we will take standard basis. Okay. So R2 is 1 0 and 0 1. Okay. And for R3, this is 1 0 0, 0 1 0 and 0 0 1. Let's call them V1, V2, V3, and let's call it Q1 and Q2. Okay. Now, what is T of U1? T of U1 is nothing but A1 plus A2. Okay, so the first position would be 1 plus 0. Okay, so 1 plus 0 is nothing but 1. Second position is anyway 0, and third is 2A1 minus A2. This is 2. Okay, so now we have obtained T of U1. We need to write them as linear combination of these vectors. So what it would be? This would be 1 times V1. So second position is empty, so it would be 0 times V2 plus 2 times V3. Okay. Now for T of U2, what we would obtain is, this is again 0 plus 1 1. This is 0, and the last one is 0 minus 1 minus 1. So this is 1 V1 plus 0 V2 minus 1 V3. Okay. Now in order to obtain the matrix, we'll write the coefficient corresponding to the first one as our first column. So this would be 1 0 2, and the second coefficient we'll write as second column. Okay, so what we will obtain? We will obtain as 1 0 and minus 1. So this is the matrix corresponding to this particular linear transformation. Okay, now here is an example. I would give you 2 minutes to try solve this. So this is quite an easy one. So you are given a linear transformation from R3 to R2. Now rather than explicitly mentioning what is this linear transformation, they have given you map of every basis element. You can see you are given T of 1 0 0, you are given T of 0 1 0, and you are also given T of 0 0 1. Okay, now they have asked you what is the matrix corresponding to this linear transformation. So I'll give you 2 minutes. I'll wait for till 6:40. Think and let me know what option you think is correct. Please type it in the chat box. Okay, somebody says second. Yeah, some more people is saying second. Yeah, others can also try. This is not very difficult. Okay, so what I said, whatever value you obtain for your first map, right, you write it as a linear combination of basis of R2. So now you have R2 on the right hand side, so you'll write it as linear combination. What you would obtain is 1 times 1 0 plus 2 times 0 1, right? So if you write these coefficients as your first column, you straight away obtain second option. So you can verify this for others also, that this is 9 comma minus 3, this is 1 comma 1, and this is how you obtain matrix corresponding to a linear transformation. Okay, So this way works for any linear transformation. Okay. Okay. Now one question that was mentioned in your assignment, I sort of covered orthogonal definition in last session, but I'll just say what is orthogonal and teach you how to solve this kind of a question. Okay. Okay. So vector v1 and v2 are called orthogonal if dot product between v1 and v2 is 0. So in the later part of this lecture, what I'll cover is inner product spaces. Okay. So rather than dot product, if you replace this by inner product between v1 and v2 equal to 0, then also this definition is correct and more generalized. Okay. So what we want is that dot product between two vectors are 0. Okay. So let's say you have some subspace. Okay. Then what is the orthogonal component of W? So orthogonal component of W means that let's say you have a subspace W, then W per or orthogonal component of W means, let's say if you take some vector v2 from here and you take a vector v1 from here, then your dot product should be always 0. Okay. If this thing satisfies, then W perp is your orthogonal component of W. So all vectors, if you take its dot product with any vectors in W, then the dot product should be 0. Okay. So this is what is meant by orthogonal component. Okay. Now one very small thing. Let's say v1 and v2 are orthogonal. Okay. Then what can you say about 2 times v1 and v2? Then 2 times v1 dot v2 would also be equal to 0. Okay. So you can use your dot product calculation to show this thing, and this is a like property of inner product space that this should also be a 0. Okay. Another thing is, let's say now v1 dot v2 is 0 and v3 dot v2 is also 0. Okay. So what I mean is, now this would imply that v1 plus v2, sorry, v1 plus v3 dot v2 is also 0. So this dot product would split, that is this v1 dot v2 plus v3 dot v2, and this would lead to 0. Okay. So why am I saying all these things? So look at the question. What does this say? Let's say W is span of these two vectors. Okay. Then you are asked to find orthogonal component of this. So what my point is, if you find a vector that is orthogonal to both of these vectors, okay, then let's say you found a vector u that is orthogonal to this and this vector, then that particular vector u would be orthogonal to any vector in linear combination of these two vectors. Okay. So if you are asked to find orthogonal component of W, what you will do is you will just look for a vector that is orthogonal to both of these vectors. Okay. So I think there is a related question in your assignment also. So in order to solve that, what you need to do is you need to look for a vector that is orthogonal to both of these. Okay. Let's look at the first vector. So let's name these vectors. Okay, let's call this v1, v2, and let's call these u1, u2, u3, and u4. So what is v1 dot u1? This is 0 times 1 minus 1. So this is minus 1 into 1, that is minus 1, plus minus 1 into minus 1 is 1. So this is 0. Okay, so v1 dot u1 is satisfies to be 0. Now let's look at the second one. Okay, so what is v2 dot u1? This is 0 minus 1 minus 1. This is equal to minus 2. So because this u1 is not orthogonal to both of them, So this particular option is cancelled. Okay. Now let's look at the second one. Okay, let's do it over here. What's u2 dot v1? This is 1, 0, and this is again 1, so this is 2. So we obtained a 2, so straight away cancel this without checking for the v2. We cancel this option. Okay. Now let's look at the third one. So this is 1, 0, 0. So u3 dot v1 we would obtain as 1. Again, this is cancelled. Let's look at the fourth one. What is u4 dot v1? u4 dot v1 is minus 1 plus 1, minus 1 plus 1 plus 0. This is equal to 0. What is u4 dot v2? This is minus 1 plus 1 plus 0. This is 0. So because now this fourth option, both of them are orthogonal to this particular vector u4, so your fourth one is your correct answer. Okay. Any doubt in this? Okay. Okay. So before going to this metric space, because I want to do this in continuity, let's look at what is meant by a convex set first. Then we will get back to that metric space, inner product space, what is meant by all those things. Okay. Okay. So okay. So let's say you have some set in R2. Okay, we'll take example of R2. You can imagine same thing in any Rn space, okay, or any arbitrary space. Okay, let's say you have some space like this. Okay, so what is meant by convex set is, okay, that if you have any 2 points inside that particular set, then the line joining those 2 points must also be inside that set only. Then those kind of sets are called convex set. Okay. So if you look at this particular example, if you take a point here and take a point here and draw a line joining these 2 points, then you can see that the line has gone outside that set. So this is not a convex set. Okay. So similarly, let's say if you have your number line, right? So if you let's say this this particular interval is your set, then if you take any 2 points in this interval, then the line joining these 2 points will always remain in that set. So this is a convex set. Now if your set, let's say, is a combination of 2 intervals, let's say it's here and here. Now if you take a point here and a point here and you draw a line joining these 2 points, then you are moving out of that set. So in your real line, only your intervals are convex set. So this is not a convex set. Okay. Similarly, you can in R3 also you can imagine that your cubes or cuboids or spheres, these are all convex sets. Okay. So if somebody asks you how whether to check a particular set is convex or not, so the best way if you can draw that particular thing is to draw that thing and see whether 2 lines that you join remains inside that set or moves out of that set. Okay. I'll just also mention the formal definition. Okay. So let's say you have this kind of a set. This, let's say this is x1, this is x2. Then what is the equation of line joining this set? So what would be the equation? Equation would be lambda times x1, this is x2, plus 1 minus lambda times x2, where your lambda belongs to 0, 1. Now if this particular set is your let's say this set is S, is a subset of S for every x1 and x2 belonging to S, then S is a convex set. Okay. So I think there is a question related to this also. So those all examples are in R2, so you can just draw those particular things. I think one of them is ellipse, right? Okay, one of them is circle. Okay, So you can try those things and get to the answer. So let's say I draw one example. Okay. So let's say I'm looking at a rectangle. Okay. This is my set, but I'm just looking at the boundary of this set. Okay. This is the boundary. I'm just looking at the boundary of this set. Is this a convex set or not? Can you please type in the chat box? Would this be a convex set?
No, this is not a convex set.
Right. Because if we take a point here and if we take a point here and join them, then this goes outside that set. Now, rather than a hollow rectangle, let's say if I fill this thing up, then this would make a convex set. Okay. Okay. So I just wanted to mention this about convex set. Okay. So this is a 2-hour long session. I think this might be a good time to take a break for 5 minutes. So this is 6:51. I'll
Sir,
start with, yeah,
I
yes.
have one question.
Mm-hmm.
There is a matrix space, mod of e to the power x minus e to the power y.
Just a second. So you have a metric space.
Yes.
Okay.
Distance d of xy equals to
Mm-hmm.
mod of e to the power x
Mm-hmm.
minus e to the power y. It
Okay.
is a matrix or not?
See, first two properties are easily verifiable over here, right? So the only thing that you would be left to check is the triangle inequality.
Yes.
Okay. Okay. Let me think about triangle inequality. So this is a metric space, right? So you know that this mod has a property that if
Hmm.
you have, let's say, x plus y, then this is always less than mod of x plus mod of y. I'm
Mod
just
of.
talking about the modulus function. Right now, I'm not talking about the metric space. So this your mod thing always satisfy your triangle inequality, right? Now, let's say you want to look at distance of x comma y. This is your e to the power x minus e to the power y. Now, if you rewrite this thing in this way, that you just subtract e to the power z and you again add e to the power z, right?
Hmm. Yes.
Then you can break it in two parts. So the way I said x plus y, so you consider this much portion as
Hmm.
x and the next half as y. Okay. So
Yes.
using the triangle inequality of your modulus, you can write it as e to the power x minus e to the power z, and again e to the power z minus e to the power y, right? So this would be less than equal to this thing. Okay. So this is nothing but distance between x comma z, and this is distance of z comma y. So you can verify the triangularity. For others who don't know what this metric space is, I'll just come to this in a minute or so. Rohini,
Thank you.
you have some doubt?
Nice, sir. Clear.
Okay.
Sir, one more question.
Mm-hmm.
Is this video recorded?
These sessions are recorded.
Okay.
I will uh, start again at probably 6:57 because this is a long session. It can be boring also. So I'll probably start at 6:57 or 6:58. So what I have left is I'll talk about probably in 15-20 minutes about metric spaces, norms, and inner product spaces, probably motivation behind them. And next 30-35 minutes, I'll try to talk about eigenvalues and eigenvectors and solve some problem based on them. Okay. Okay, probably I'll start. Okay, so yeah, so first thing that we are going to cover in this portion now is something called as metric spaces. Okay, so what actually a metric space is, uh, like it is a generalization of distance that we know. Okay, so let's say uh, like till our school, let's say you are given 2 points. Let's take very simple example, 1 and 2. Let's call this x1, and let's other point be 2 comma 1. So or maybe just erase this thing. Okay, let's say you have this point as 1 comma 0. Okay, and this point also as 0 comma 1. So if I ask you to find distance between these 2 points, the uh, first thing that would come to my mind also is, let's draw a line. So length of this line would be the distance between these 2 points. Okay, so that is what is called as the Euclidean distance. So you would take square root of 1 minus 0 square plus 0 minus 1 square, and you would come up with something as square root of 2 as the distance between these 2 points. Okay, so I have a map of a place called Dwarka in Delhi. So let's say you want to go from this particular point in Dwarka sector 10. Okay, or probably let's say you want to go from this Welcome Hotel ITC. Okay, to let's say this particular point. Okay, so now if I have to calculate the distance between these 2 points, and let's say I do it via a straight line between these 2 points, then that won't be feasible to me, right? I can't drive my car in this way, or I can't just take any public transport that goes above the building. So this notion of distance that we studied in our Euclidean space make no sense, make very less sense in real life. Okay, so in real life we might have some other kind of distances, right? So for example, in this case, if I take length of this particular road, okay, and then add it to length of this particular road, then I would obtain my distance, right? So this is the motivation behind metric spaces. So what we want to do is we want to define sort of distances that sort of preserves the or sort of generalizes the definition of Euclidean distance. Okay, so we will do that. So before doing that, let's look what would be this distance over here. Okay, so let's say uh, you want to find the distance between these 2 points. Okay, what you did is you went this way and then again went this way. Okay, so if your this was, let's say, your x-axis. Okay, this particular line was your x-axis. Okay, x-axis, and this particular line was, let's say, your y-axis. Okay, then what would have been the distance? So let's say this is uh, x comma 0, this is 0 comma y, then the distance would be x plus y, right? So this is mod of x plus mod of y. So this distance actually exists, and this is called Manhattan distance. So roads in Manhattan are very very grid form. So from anywhere you can reach anywhere using this kind of method. So this is something called as Manhattan distance. So how is it defined? So let's say you are at point x1 comma y1, and you want to go to x2 comma y2, then the distance is defined as x2 minus x1 mod plus y2 minus y1 mod. Okay, so this is just a definition of Manhattan distance. Similarly, you can have many distances. One of them was question asked as a doubt. So distance between x comma y can be given as e to the power x minus e to the power y. Okay, so, when you would use this kind of distance, so if you look at your exponential function, it grows very rapidly as compared to your linear function, right? So when you want a distance between very close points, so if let's say my x and y are closed on number lines, but I want the distance to be scaled. So then you can use these kind of distance, so that you take this to the power of something, and then you evaluate the distances. Okay. Okay. So here is something that is called as metric spaces. So what is a metric space? Metric space is nothing. It's a function. So D is nothing, a function from x cross x. So what is the input of a distance function? The distance function will take 2 points, right? It will calculate distance between 2 points. So it's a map from x cross x to real number. And if you look at more carefully, this would be just the positive half of the real number, including 0, because distance can never be 0, right? So it is a map from x cross x to R, which satisfies these three properties. Okay. So the first one is your positivity property. So what does it say? That distance between any 2 points should always be greater than equal to 0. Okay. So the distance between any 2 points must be greater than equal to 0. And when it can be 0? It can be 0 if and only if your x and y are same points. So if your x and y are not the same points, then the distance can't be ever be equal to 0. This is quite intuitive, right? Now the next point is that if you take distance from x and y, or you take distance from y to x, this should be same. Okay. So distance between x to y must be equal to distance between y to x. This is called the symmetric property. Okay. And the last one is that this is called as the triangle inequality. And when you are proving some function to be metric, this kind of becomes the most tricky, or I would say the important part to check. So this is something called as triangle inequality. So what does it say is that, let's say if you want to look at the distance between x and y, okay, and if you look at some other points also z, okay, then if you connect these 3 points, then they would form a triangle, right? So you know that in a triangle, sum of two sides must always be greater than equal to the third side. So this is what this particular property is forcing, that if you look at the distance between x and y, that should be always less than the sum of other two sides of that particular triangle. Okay. No matter what z you take, if you take even over here, okay, then also this thing would be satisfied. So this is for any arbitrary z that you take. Okay. So if any function satisfies these three property, you can call that function as a metric. Yes, Praveer, these sessions are recorded. You can find the link in discussion forum as well as on the course webpage. Okay. Okay. So here is an example of another metric that is called discrete metric. Okay. So what is discrete metric? So distance between x and y is 0 if your x is equal to y. Okay. And it is 1 if your x is not equal to y. Okay. Now, uh, uh, this is one example. So let's try and verify this particular example. Okay. One more thing, if at any point some color pen that I'm using is not very clearly visible on your screen, please let me know, right? So that I change the color, because I keep changing the color. So somebody is asking, sir, D is the distance from x to y, or these are coordinate points? No, D is the distance between x to y. Okay. So D is a function that takes 2 points, x and y, and then calculates the distance in real number. Okay. Okay. Now let's see what was the first property. First property was that d of x and y must be always greater than equal to 0. Is this thing satisfied over here? Yes, this is always greater than equal to 0. And when is it equal to 0? If and only if x is equal to y. So that particular property is also satisfied over here. So isn't discrete metric basically a circle with either distance as the radius or 0? Yes, you can take this one as any other radius also. So if you look at the geometric representation, then you would get a circle, right? That's possibly correct. Not even a circle. So actually what you are saying is, so every point would be mapped to, so if you look at the 2 points, okay, so how do you obtain those kind of circle that you're talking about? So let's say this is your origin, okay. What in those kind of diagrams people do is they sort of draw points that are at a particular distance from origin, okay. So for example, for Euclidean space, okay, what people do is if you draw points that are at distance 1, what you would obtain is you would obtain a circle. I think that's what you are referring to, right? But in case of discrete metric, if you draw these kind of things, so let's say what are the points which are at distance 1 from origin, then it would be your complete space, okay, except for 0. So this 0 is excluded. So actually you won't get a circle, but you will get the complete space, geometrically speaking. Okay. Okay. So let's get back to proving this thing. The first property is very much satisfied for our metric space. Second property was d of xy is equal to d of yx. This is also very straightforward, right? So we are done with it. So third property is something that is interesting. So d of xy is less than equal to d of xz plus d of zx. Okay. Now, on the left hand side, we can have two possibilities. Either my x and y are same points, or my x and y are different points. If they are same point, then this thing would be 0. If they are different, then this thing would be 0. Okay. So let's try looking at the first case when they are sort of case 1, when x is equal to y, then d of xy is 0. Okay. Now, because they are same point, now on the right hand side again we have two possibilities. Okay. Either z is equal to x is equal to y, or z is different from these two, right? Now, if my z is equal to x and y, then what is my this thing and this thing? So distance of x comma z would also become 0, and distance of x this z, this should be y, sorry, this is y, this would also be 0. So left hand is always already 0 and right hand should be 0 plus 0. So this thing is satisfied, right? Now for the other part where z is not equal to x and y, right, then what would happen is that d of x comma z is 1, d of z comma y is 1, and 0 is less than equal to 1 plus 1. So then also this property is satisfied. Okay. Similarly, when you have the case when your x is not equal to y, right, then also you can split this z thing in different cases, and you can verify that your triangle inequality would be satisfied. Okay. There is a particular reason why I took this particular example. So when we'll do norms, we will understand why I took this particular example. Okay. Any doubt with the definition of metric space or how we can prove a metric space? So anything that you want to ask about it? Rohini, yes, you can unmute yourself.
Sir, I have one question.
Mm-hmm.
Is assignment system has negative marking?
I am not very sure because I am not checking the assignments. So are you on discussion forum? Okay, somebody says no negative marking, so I think he might be correct. Or you can
Or
just post it on discussion forum. The official TA would confirm that thing, I think. Or I can also check. and confirm if you post it on discussion forum.
Okay, sir.
Okay. I am not very sure about this, sorry. Okay. Okay. Now, what we have done so far is that we have a generalization of notion of distance between 2 points. Okay. So earlier we knew till our school days we only knew one kind of distance, that was Euclidean distance. Now what we know is that we can define almost infinitely many distances using that satisfies some particular properties. Okay. So the next sort of generalization is for length of a vector. Okay. Till now, whatever length we have been calculating, that particular length is called your uh, yes, that is called as your Euclidean length or L2 norm that we call. So we will look beyond that. Okay. So the same way as the generalization of distance was called metric. So if you look at the generalization of length, we call them as norms. Okay. Now we call them as norms. So what is a norm? Norm is a function, okay, that would take a vector from your vector space and give its length in R. Okay. Now this also must satisfy some properties, right? What are those properties? First property is length of any vector must always be greater than equal to 0, right? This is very obvious, right? You don't want length of a vector to be negative. Okay. And the second thing is the length will be 0 if and only if that particular point is 0 itself. So if you have any non-zero point, its length should be a positive integer. Oh, sorry, positive number, not integer. Okay. Now the second property is, let's say you have some vector x, okay, and you scaled it by, let's say, factor 2. You doubled its length, right? So its length must be double the length of the original vector. So this is what this thing is saying. Let's say if you scale this by a factor a, then the length gets scaled by a factor, that same factor. Okay. So why is this mod over here? So let's say if this was your vector and you scaled it in opposite direction by length 2, still its length is 2 times of this, right? So that's why this mod comes into picture. And now the third property is your triangle inequality again. Okay. So length between so the length of x plus y must always be less than length of x plus length of y. So this property was earlier satisfied by your mod, that mod of x plus y is less than equal to mod of x plus mod of y. The same property we translated into norms. So any function from a vector space to R that satisfies these things is called a norm, or these are the generalization of your length. Okay. Now you have a question in assignment related to this, so I'll cover those things. Okay. Let's say, I think I covered it last time also, but I'll cover it this time also. Let's say you have some vector in Rn. So let's look at some popular norms that you can have. Okay. So first one is your L2 norm, or 2 norm some people call it. Okay. So this is the most common norm that you have been studying from your childhood. Okay. So what is it? Let's say you have a vector 1, 2, 3. Then what is 2 norm of it? So 2 norm of this x, or let's say you have some x which is equal to x1, x2, x3. Then what is 2 norm of x? This is square root of x1 square plus x2 square plus x3 square. Okay, this is a norm. So what would be the norm of this thing? This would be square root of 1 square plus 2 square plus 3 square. This is 9, 4, 13 plus 1, 14. This is square root of 14. Okay. So this is called as 2 norm. 2 norm. Okay. Now, because we have 2 norm, we have something also called as 1 norm. Okay. What is 1 norm? 1 norm is nothing. So if you have same, now we will be talking about same x for other examples also. So what is norm of x? norm of x, this is one norm. So you write a subscript to denote what kind of norm it is. Okay. So if you have one norm, what it is, this is mod of x1 plus mod of x2 plus mod of x3. So what is one norm of this particular thing? This would be mod of 1 plus mod of 2 plus mod of 3. This is equal to 2 plus 1, 3, 3, 6. Okay. Okay. Now you also have something called as p norm. So right now we just talked about 1 and 2. So you can have norm defined for any particular positive integer. You can just denote it by p norm. Okay. So what is p norm? So if you look at this thing, what was happening is we were taking it to the power 2, and towards the end we were just square rooting it, right? So now what you will do is you will do x1 to the power p plus x2 to the power p plus x3 to the power p, and after you have added them, you will take power 1 by p, that is pth root of this particular sum that you have obtained. Okay. For example, let's look at the same thing, 1, 2, 3. So if you take 3 norm of this thing now, okay, this would be 1 cube plus 2 cube plus 3 cube to the power 1 by 3. Okay, so this is 27 plus 8, that is 35 plus 1, 36. So this will be cube root of 36. That is the 3 norm of this particular vector. Okay, and there is one more norm that is called as the infinity norm. So I think all these norms are there in the question that is asked. That's why I'm mentioning. So there is something called as infinity norm. Okay. So what is infinity norm of this? This is maximum of mod of x1 comma mod of x2 comma mod of x3. Okay. So let's take the same example of 1, 2, 3, or maybe we can, yeah. So what is the infinity norm of this thing? This is max of 1, 2, 3, that is 3. Okay. Any doubts in norm? Okay. So one thing, if you look at let's say you have some point, let's say x1. Okay, people are joining. Yeah. If you have some x1, let's call it x. Okay. If you have, let's say, some x equal to x1 plus sorry, x1 x2. Okay, then what is the Euclidean length that you use to calculate for this? That is 2 norm. This would be x1 square plus x2 square, right? And now if you have some y, that is y comma y2, then again this y of 2 would be y1 square plus y2 square. Now if somebody asked you to find distance between x and y in Euclidean sense, what it is? So distance between x and y would be under root of x1 minus y1 square plus x2 minus y2 square. Right? Can you draw some relation between this formula and this formula over here? So what actually is happening is, if you look at it carefully, distance between x and y is nothing but the length of x minus y. Okay, so if you do x minus y, it would be x1 minus y1 and x2 minus y2, and then if you put it that thing in this norm formula, it's exactly the same thing that you would obtain. Okay, so if you have any norm, right, if you have a norm, what you can do is, from that norm you can obtain a distance. Okay, so let's say you have some norm. Okay, then corresponding to this norm you can define a distance by norm of x minus y. Okay. So if you look carefully, now using the one norm, you would have obtained the Manhattan distance that we talked about initially. Okay. Right. So, okay. Now there is one more question over here. Like for every norm, you have a corresponding distance. Okay. How do you obtain that? That you just use this formula to define the distance between x and y. Okay. Now is the other way around true? So the question is, like, if you have any distance, is it always derived from a norm? Okay. Derived from a norm. Okay. So the answer to this question is actually no. So there are distances which need not be necessarily derived from a norm. So so we need to produce at least one distance that can't be derived from any norm, right? So the example for that is length of a arc. I didn't get your question, Kushal. Can you please be more specific?
Sir, I'm
Mhm.
giving the example of whatever you're saying, that
Okay.
distance which we cannot derive from a norm.
So what do you mean by length of arc? So let's say if I have 2 points x and y, what do I do next?
I mean to say that we cannot represent this in the form of a p norm.
Yeah, maybe. But what I meant was that not only these p norms, but any norm that can satisfy these particular properties. Okay. So yeah. So one example that I would give you is example of this discrete metric that we did. Okay. So what was our discrete metric? The distance between x and y is 0 if x is equal to y and 1 if x is not equal to y. Okay. Now let's say uh, think that if this was derived from a norm, okay, then uh, what would have happened is, so norm has this property, if you remember, that norm of ax is equal to mod of a norm of x. Okay. So now let's say you have some distance between x and y. What is the value of distance between x and y? This is norm of x minus y. And the distance would always be 1 if, let's say, x is not equal to y. Now what would be the distance between 2x and 2y? The distance would be 2x minus 2y. Now we can take 2 common, right? This is x minus y. So this is 2 times 1. But what we know is that for discrete matrix, the distance would always remain as 1. So this this explanation leads us to the conclusion that this discrete metric cannot be derived from any norm, not only p norms, but any possible norm. Okay. So this is a one-way relation. So from norm, we can obtain metric, but the other way is not true. Okay. Okay. Any doubts in this? Okay. Okay. Now we would move to, so we talked about generalization of distances. We talked about generalization of length. Now, last thing that is left is we will talk about generalization of angles between two lines. Okay. So how do we define the angles? So let's say you have some vector x, or let's call them v1 and v2. Okay. Let's say you have some vector v1 and some vector v2. Then how do you use to find the angle between these two? So what you used to do is that your v1 dot v2 is equal to norm of v1 norm of v2 cos theta. So you used to take this thing on this side, then you would obtain some value of cos theta is equal to norm of v1 v2, and on the top you have v1 dot v2. Okay. So this is what you used to do for finding the angle. Now what we will generalize is this notion of dot product itself. Okay, rather than directly generalizing the angle, what we will do is we will generalize this notion of dot product between two vectors. Okay. Okay, so this is something that is called as inner product and generally represented by two this angled brackets. Okay, so if you have something like this x comma y, this means that this is angle between this is dot product between x and y. Okay, or a generalized form, that is inner product between x and y. Okay. Okay, so again your dot product satisfies some properties that you can remember. Okay, so what is the first property? So if you look at your dot product, okay, so now we did this some moments ago in our calculation. Let's say you take x plus y and you take its dot product with z, then it splits, right? This is x dot z and plus y dot z. Okay, so the same property we are expecting out of here also. Okay, so if I have x plus z and I take its inner product with y, then it should split, right? So this is x and y plus z and y. Okay, now the second property is, let's say if I have cx and I take its dot product with y, then I can take my c out, right, and then just calculate x dot y. Okay, so the same thing is over here, that if you have cx and you take its dot product with y, then its dot product must be c times x dot y. Yeah, Rohini, you have some doubt?
Yes, sir.
Mm-hmm.
Uh, if we have to obtain an angle between 2 points, then
Yes.
this is the formula cos theta equals to something.
Yeah.
So angle theta is an angle, means cos inverse goes to right hand side,
Yes.
and we have to find the value of theta, right?
Yes.
Okay, sir.
Yeah. And you would like sort of see that thing, this thing also, that because you are dividing by norm of v1 and v2, the values that you will obtain would always be in -1 to 1. So the cos inverse would also exist. Okay. Yeah. So coming back to what we were doing, so what is the third property? Third property says that if you take dot product between x and y, okay, and if you take now dot product between y and x, now see, you are talking about angle, right? Let's say, yeah, you have these vectors, okay. Then the way you are moving, let's say this is my x vector and this is my y. Now the way you are moving from x to y, and if you are moving from y to x, so although the value of angle is exactly same, but the orientation has now changed, right? So this thing don't make a lot of difference when you're talking about real space R2 or R3, when we are when we are like worried about our angle theta, but in complex space this can make some difference. Okay, so what does the third point say is, if you take inner product between x and y and you take inner product between y and x, then they are complex conjugate of each other. This hat that I have drawn on the top, this is complex conjugate. Okay, so this is third property of our inner product. And the last property is again sort of intuitive, that if you take dot product of same vector with itself, it should be greater than equal to 0 as soon as far as if your x is not equal to 0. So if you remember, if you take any non-zero x and you take its dot product of itself, it would give you length of that vector, that is norm of that x, right? So that should be non-zero, that should be greater than 0 if your x is not 0. Rohini, did you again raise your hand?
No, sir. I have one question, but I will ask in later.
Okay, so yeah, so these are the four properties associated with inner product spaces. If some function satisfies this property, then you can call it as inner product. Okay. Now, in the last point, I sort of revealed this thing. Uh, yeah, so when you had a dot product, so if you took a dot product of a vector with itself, it used to give you the length of that particular vector. If you recall, let's say, eh, oh, just a second. If you have, let's say, x1 and x2 as your x, then what was the length? Length was x1 square, right, plus x2 square. Okay. Now, if you look at x dot x, what would it give? X1 square plus x2 square. Is there any relation between these two? Definitely there is. What it is, that your inner product between the same vector is nothing but the norm square. Okay, so if you take square of this, you would obtain this. So now again, if you have any inner product space with you, then from that you can define a norm for a particular vector, right? How is that defined? So norm of x is nothing but square root of inner product between those two vectors. Okay, now again the same questions comes to us. So now, as in case of norm, from norm we can obtain metric, right? Now what I'm saying is that if you have an inner product, you can obtain norm from it. Okay, now we saw that this way it is not true, that from any metric it is not necessary that it has been derived from some norm. Now what is the case over here? The answer is, over here also this is not true. So if you have some norm, it is not necessary that it has come from some inner product space. Now I will just give you a hint in lack of time. So if you want to see, so I mentioned 3-4 norms over here. That was L2 norm, L1 norm, LP norm. So any norm except of L2 norm is not derived from inner product space. How you can check is, so any norm space will satisfy a property that is called as parallelogram law. Okay, you can check this out if somebody is interested. So these inner product spaces do not satisfy this parallelogram law, need not satisfy for all the cases this parallelogram law. In fact, for these norms that I mentioned, that is P norm, for P not equal to, this is not satisfied. Okay, yeah. Okay, so for norms and these matrices, I had this much. Any doubt till now before I get into this eigenvector and eigenvalue kind of thing? And yeah, hello.
Hello.
Yeah, you have something to
Um,
ask?
yes, sir. I have one question.
Mm-hmm.
If we have a set A which contain element x and y belongs to R2 such that x square plus y square is greater than equals to twice x. So
Can
how
you
can this
just
on
can you please repeat the set? So you have a set A which
A
contains.
contain element x and y belongs to R2,
Mm-hmm.
R2
That is
sorry,
fine.
such
R2.
that
Mm-hmm.
x square plus y square
Mm-hmm.
greater than equals to 2, and
2.
we have to complement of this set, then how can we approach twice x, sorry, is
So
greater than equals to twice x,
mm-hmm.
and we have to find the complement of this set.
Complement in sense. So complement in R2.
Complement of a
Complement of.
s complement of a in R2.
Yeah. Okay.
So how can we approach for this type of question, sir?
So this is, I think, quite simple one. So what you have you have been given a condition over here, right? So
Hmm.
x square plus y square, this is greater than equal to 2x, right? So what I can see directly is, so if you take x square minus 2x plus y square, this is greater than equal to 0. Okay. So if you will just complete the square over here, So it would get into form something x minus a square. Okay. And you, okay, so probably I'll just give you a small hint. I won't solve it completely, right? Yeah, because this is not very related to what we are doing. So if you look at this thing, that if you just x square plus 1 minus 1 minus 2x plus y square is greater than equal to 0. Okay. Now if you just look at these terms, is it a square plus b square minus 2ab? So what is this for? This is x minus 1 whole square plus y square. Okay. Minus 1 is greater than equal to 0. You can take this thing on this side, and what you would obtain is this is greater than equal to 1. Okay. So
Yes.
now this is nothing but a equation of a circle centered at 1 comma 0, right, of radius
Yes.
1. So what would be its complement? So the area outside that circle.
Yes, sir. Thank you, sir.
Okay. 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 So yeah, we have prox 20 minutes left. So before going into this eigenvalue eigenvector, I have some one or two questions that is related to what is there in our assignment. So I'll try to solve those things. Okay. Now this question talks about positive definite or positive semi-definite and indefinite matrices. Okay. So professor has already included 2-3 definitions of positive definite, positive semi-definite. I'll just repeat this thing. Okay. I'll just very briefly repeat and use one of those points to obtain my answer. Okay. So, uh, so let's say I have a vector. Uh, so I have a matrix A. Okay. A. If first point is for every x. Okay. X transpose AX is greater than equal to 0. Then this kind of matrix is called as a positive semi-definite matrix. Okay. One thing is that my A I am assuming to be symmetric matrix. Okay. Now, if this X transpose A, X was strictly greater than 0, then we would have called it as positive definite matrix. Okay. Now the third is, if this was less than equal to 0, then it would have been positive negative, so negative semi-definite matrix. Okay. And if it was strictly less than 0, it was negative definite matrix. Okay. Last point is that if none of them is true, then we will call this kind of matrix as indefinite matrix, that we don't know much about them. Okay. Now this is a basic definition. Okay. Then it has also some properties related to it. So if you want to check, rather than calculating this for every arbitrary x, what we can do is we can check via eigenvalues. We will just get back to what eigenvalues are, and that would be more clear to you. Okay. So let's say this matrix has two eigenvalues, lambda 1 and lambda 2. Okay. Now if both of them are greater than equal to 0, then we will call, based on the sign of our eigenvalues now, if both of them are greater than 0, then it is positive semi-definite. Okay. If both of them are strictly greater than 0, if they are strictly greater than 0, then it is positive definite. If it is less than equal to 0, negative semi-definite. If it is strictly less than 0, this is negative definite. And if let's say lambda 1 was 2 and lambda 2 was minus 3, so their sign don't match, then in that kind of scenario, it would be indefinite matrix. Okay. So one characterization was via the definition, and the second characterization is via eigenvalues. Okay. Now there is a third characterization via pivots, and that is, I think, the most simple way to solve this kind of question. So what are pivots? Let's say you have a matrix, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. So this matrix will have 3 pivot elements. Okay. What is my first pivot element? You just look at the extreme left point. So this, whatever you have obtained, is a 1 cross 1 matrix. So if you look at its determinant, that is your first pivot. Okay, that is your first pivot. Okay, now you increase its size. Okay, now if you look at the 2 cross 2 matrix from the top left side and you obtain this determinant, then it is your second pivot. Okay, and what is left now? You will look at the complete, right, the complete matrix. Now if you look at this determinant, this is called as your third pivot. Probably bad choice of color. Yeah. Now same way as it was in your eigenvalues, if you look at the sign of these pivots, if all of them are positive, okay, that is greater than equal to 0, then it is positive semi-definite. Now if it is strictly, then it is positive definite. If it is less than equal to 0, then it is negative semi-definite, and so on, right? So we will solve this particular thing the same way, right? Okay, so we have been asked to check whether it is positive definite, positive semi-definite, or those kind of things. Okay, now we will look at the first pivot. Okay, so what is its first pivot? It is 6. So what would be its determinant? Pivot 1 is 6. Now what will the pivot 2? Pivot 2 would be the determinant of this matrix. What is its determinant? 6 into minus 5 minus 30 minus 16. What it is? Minus 46. So this is plus, right? This is minus 46. Do their signs agree? No, they are opposite of each other. So what would be the correct option? That it is an indefinite matrix. So you have a similar question in assignment. You can just check the pivot elements, and then you can just see what happens. Okay. Okay. So I think you have a question, but in want of time, I wanted to do this complete question, but because we have to do eigenvalue and eigenvector also, I'll solve only till the part that you need for your assignment right now. Okay. Okay. So the question is, let's say you have some vector space X, sorry, some vector X, and you have to find its projection. Okay, so uh, so you have to find its projection into a subspace L that is spanned by some orthogonal vectors. Okay, so here you have only one vector. Let's say you had two vectors, like W is spanned by, or let's say you had L is spanned by, L is spanned by, let's say something like 1 0 and minus 1 0. Not very good. So let's say 0 1. Okay, so you want to find let's take one more 0 over here. Yeah. Okay, so somebody asks you to find the projection of some vector X into this space L spanned by these two vectors. Then how do you go about that? Okay, so it's a very simple thing. Let's say this is V1, this is V2, and you have to find projection of X. Then what you do is you do X dot V1 divided by V1 dot V1, that is norm of V1, into V1. So what this particular quantity over here represents is, this is the portion of X that is inclined in direction of V1. Okay, so this is projection of X onto V1. Okay, now the second part is X dot V2 divided by V2 dot V2 into V2. Okay, so this is what you need to do when you have more than one vector. Kushal, when we will go to the portion on optimization, then this will be, you would very much appreciate why do we need to see a matrix to be positive definite or positive semi-definite. Okay, so there we have many great results. I don't want to spoil it for you right now, but this is very much used in optimization, and optimization in terms is very much used in machine learning these days. So that's why we need to know whether a matrix is positive definite or semi-definite. Another thing is, one more point is there, that sometimes it is easier to prove that a matrix is a positive definite or a semi-definite rather than proving that a matrix is like invertible. So in proving a matrix to be invertible also, this kind of becomes sometimes handy. Okay. So I think when we are doing regularized linear regression, so you obtain a matrix something as x plus lambda I inverse, yeah, something over here. So, proving this matrix also, the most popular approach is to prove that this matrix is positive definite, or those kind of things. So I think you will appreciate it more when we reach to the optimization part in later weeks. Okay. So getting back to this question, so what is asked over here is that we have to find the projection of this particular x uh, onto the space spanned by this thing. Okay, so we'll do it straight away. So this would be x dot u divided by u dot u times of u. So what it is, minus 6 into 3, this is minus 18 plus 8 divided by norm of u, that is 9 plus 4, okay, norm square, sorry, times of 3 2. So what is this? This is minus 10 by 13 times 3 2. So this is your simple answer. So if you had one more, let's say v over here, that was equal to, let's say, minus 2 comma 3, yeah, minus 2 comma 3, then you would have one more term over here and you would have obtained your answer. Okay. Okay. So now we have some 10-12 minutes that we will devote to understanding what are eigenvalues and eigenvectors. Okay. So yeah. So one very small thing. So this linear algebra we are studying in context of using it for machine learning, but the way this thing started was that people wanted to solve a system of linear equation. Okay, so that's how the area of linear algebra developed. So let's say you have a system of equation like this: 1 0 0 2 x1 x2 is equal to 2 comma 4, and you have a system of equation 1 2 3 4 x1 x2, this is some 8 10 etc. So what one like, just at looking at it, which one do you think is easier to solve among the two? Okay, anybody would say that this particular system of equation is easier to solve, because you can straight away say that x1 is 2 and 2x2 is 4, so x2 is 2. Here you will have to do some elimination and those kind of things, then you will reach to the answer. Okay, so what people thought is, when I talked about matrix representation of a linear transformation, I told you that the matrix representation would depend on the choice of basis that you have. Okay, so we selected the standard basis, so we got one particular matrix. Okay, so if we would have selected some other basis, we would have got some other matrix. So what people asked now was, does there exist some particular basis for which the matrix that we would obtain is a diagonal matrix? Okay, so that was the question. So what they said is, so if we have some basis for which this transformation gives you a diagonal matrix, is that kind of basis possible? Okay, so the answer is sort of, it is not possible for every transformation. It is possible for some transformation and it is not possible for some transformation. So what we want is that our T of beta is a diagonal matrix, and if that kind of matrix exists, how do we find it? Okay, now let's say your T was a map from V to V. Okay, right, and let's say you were able to find a basis for which this T of beta is a diagonal matrix. Then what would have happened? Let's say this is your basis set, that is B1, B2, Bn. Okay, now let's say if your T of beta 1 is something, okay. Now when you write its coefficient, now on the both side I have selected the same basis beta, okay. Now if you want to write the coefficient, what you want is that only first position should be non-zero and everything should be 0. That's how you make a diagonal matrix, that you have non-zero entries on diagonal and 0 everywhere, okay. So whatever value you are obtaining for T of beta, what that should be? That should be lambda times of beta 1. So let's say this value is lambda, so plus 0 times every other beta 2, beta 3, 0 times beta 3, and so on, okay. So this is what you should have obtained. So this is a property, right, that if you have any vector x satisfying T of x is equal to lambda x, and then you collect these kind of x and form a basis, then that particular basis will give you T of beta as diagonal matrix. So here is where the journey for this eigenvalue and eigenvectors begin. So then people later call this particular property. So if you have a lambda that satisfies T of x is equal to lambda x for some non-zero x, because in basis you want just your non-zero elements, so zero vectors can't be a part of your basis, right? So if you have some lambda which satisfy this property for some non-zero x, then lambda is called eigenvalue for T, okay, and your x is eigenvector corresponding to lambda, okay. So I sort of complicated things for you. So for those who want easier definition, it's a very easy definition. Lambda is eigenvalue for T if T of x is equal to lambda times x for some non-zero x, and x is called eigenvector. Okay. Any doubt with respect to definition of eigenvalues and eigenvectors? If the definition is clear, then we would be able to solve this, right? Okay. So now I'm sort of going very step by step. So what we want is that T of x is lambda x. Okay. If I push this thing on the left hand side, what does this mean? T of x minus lambda x is equal to 0. Or if let's say I write it in matrix form, what does this mean? Tx minus lambda x is equal to 0. Okay. And if I now take x common, what am I left with? T minus lambda I times of x is equal to 0. And what I want is that I should have a solution to this, and my x should be non-zero. Okay. When can I get a non-zero x? If determinant of T minus lambda I equal to 0. Okay. If this particular thing was a full rank matrix T minus lambda I, then the only solution would be 0 vector. If I want a non-zero vector, then this particular thing on the left hand side must not be full rank. When it's not full rank, what should I get? The determinant of T minus lambda I should be equal to 0. Okay. So you should just remember two things from here, that you call lambda as eigenvalue if Tx is equal to lambda x for some non-zero x, and x is called your eigenvector. And how do you find it? You find it using this formula, that determinant of T minus lambda I is equal to 0. So even if you didn't understood the full story, you can just revisit this, but you should remember these 2 points at least. Okay. Now in leftover time, we'll try to solve at least one example where we have to find eigenvalue and eigenvector. Okay. So I'll take this particular example. I have to find eigenvalues and eigenvector, let's say. Okay. Now what I said is that determinant of t minus lambda I should be equal to 0. Okay. So over here my t is a. So what we'll try to solve is that determinant of a minus lambda I is equal to 0. So how would a minus lambda I look like? So lambda, this is 1 1. Okay, let me write for the first problem, let me write 1 1 4 1 minus lambda 0 0 lambda. Okay, so what does this mean? This is 1 minus lambda 1 4 1 minus lambda. This thing is equal to 0, right? So what does this mean? This means that 1 minus lambda square minus 4 is equal to 0. So this is lambda square plus 1 minus 2 lambda minus 4 is equal to 0. Lambda square minus 2 lambda minus 3 is equal to 0. Then lambda square minus 3 lambda plus minus 3 is equal to 0. If I take lambda common, lambda minus 3 plus 1, lambda minus 3 equal to 0. So what are the values of lambda that I obtain? So lambda is equal to 3 and lambda is equal to minus 1. So you can just take this thing common over here. Okay. So using this system of equation, using this quadratic equation, we obtain two values of lambda, that is lambda is equal to 3 and lambda is equal to 1, and these are my eigen values. Okay. So just a quick takeaway. So what you are going to do is, so if you have a matrix A, you are just going to find determinant of A minus lambda I and equate it equal to 0. And when you are solving this thing, whatever values of lambda you get, those are your eigen values for that matrix. Okay. So now if you have to find eigen vectors, I'll just find for one of them. Okay. So what I said, that Tx should be equal to lambda x, or t minus lambda I, x should be equal to 0, right? This is what I said. Now we have already found what is the value of lambda over here. Let's say for lambda is equal to 3, we want to find the eigenvectors. Okay. So what is A? A over here is 1141, 1141, and what is 3 lambda? 3003. So this is minus 2, 1, 4, minus 2. Okay. So what we have to solve now, t minus lambda I we have obtained. So what we have to solve is minus 2, 1, 4, minus 2, x1, x2 is equal to 0. Okay. So if you will see carefully, both of them are sort of linearly dependent. So even if you solve one of them, so this is minus 2x1 plus x2 is equal to 0. This would mean x2 is 2x1. Okay. So when you sort of solve a system of equation for your linear, eigenvectors, you will not get a unique solution. Okay. So eigenvectors, so if let's say x is an eigenvector, then 2 times x is also an eigenvector for the same eigenvalue. So eigenvectors generally are not unique. So we just observe a property that they satisfy. For example, over here what they are satisfying is that x2 must be 2 times of x1. So we can write any vector that would satisfy this property. So let's say if my x1 is 1, then x2 is 2. So this 1 comma 2 is an eigenvector corresponding to lambda equal to 3. So yeah, this is how we find eigenvalue and eigenvector if we are given with some matrix. Or if you have some transformation, you can convert it to matrix and then use these methods. Any doubt in this thing or anything that we have covered till now? Anything you want to ask? Yes, so if you go to this course web page, so there is an option called problem solving session. When you click on it, it redirects you to an Google Sheet. There you have links to all these notes as well as the recorded sessions. Okay. Even on the discussion forum, I have included the YouTube channel link where these videos are getting uploaded. You can so in the description of those videos are also the links to these notes and everything. You can access them there. Rohini, did you raise your hand?
Yes, sir. I have one question which is
Mhm.
not connected to this topic. Can I